Hey guys, today we'll be talking about the electron transport chain, also known as the respiratory chain. So before we talk about the process and what actually happens, I just want to give you a general idea of where does the electron transport chain happen. So we have a mitochondria over here, we have the outer membrane and the inner membrane, and in between is the intermembrane space, and the electron transport chain occurs here where the inner membrane is located. So the purpose of electron transport chain is ATP. This is the energy used by the body, so this is the currency of energy, and it's also responsible for heat productions, such as in infants where we produce heat using the electron transport chain. We'll talk about it. So is this process aerobic or anaerobic? Meaning, does it use O2 or does it not use O2? So oxygen is essential for the electron transport chain to work, and if there is no oxygen, the chain won't work. But to understand this more, we'll talk about it so you could understand how we use oxygen in the process. Okay guys, before we get into the details, I want to give you a really simple idea of what happens in the electron transport chain. So we have the matrix, which has some protons inside of it, and we have the intermembrane space of the mitochondria, which has protons, but I hope my photos represent that. But the protons in here are actually more than in here. And our goal, as I mentioned before, is to make ATP. So how do you make ATP? We accumulate protons in here, the intermembrane space, and we allow the protons to move and return through the ATP synthase into the matrix, where we have ADP plus inorganic phosphate. This is inorganic phosphate. They give us ATP. So this is the process that occurs. And I want you to think of ATP synthase as a motor. So the ATP synthase uses 4 protons, meaning when we have 4 H plus paths, it kind of turns like that, and it allows ADP plus PI to form ATP. So it gives us that turn that we need in order to make ATP. So this is the process in a simple way. But if we don't give protons to the intermembrane space, we're going to run out of protons. So what do? We have a pump. This is a proton pump. It moves hydrogen protons against the concentration gradient, meaning we have a low concentration in matrix and a high concentration in intermembrane space. So we pump protons from low to high, low to high, low to high to keep the concentration gradient here high, and we make them return in the area that we want, the desired area, which is the ATP synthase. Now once they return in here, they make an ATP. And you may ask, why don't they just return like through the inner membrane of the mitochondria? Why do they have to return from here? You see, the inner membrane of the mitochondria is not permeable to everything. So it's not really permeable to the protons, meaning it doesn't allow them to return. So we use a pump to get more protons inside of here, and we make them move along this area so they could return through the ATP synthase, which is also complex 5. Now we have 4 complexes, which we will talk about in this video. But you may ask, using pump requires energy. Where do we obtain this energy from? Is it from ATP, or what kind of energy do we use? So this is where redox reaction comes into play. You see, the redox reactions, which I will explain right now, give us the energy needed to allow for protons to be pumped across the matrix to the intermembrane space. So let's explain the redox reaction. Okay guys, so we have the redox reactions, and if we divide redox into 2 words, we have reduction and oxidation. Oxidation is removal of H or electron, and or addition of oxygen, while reduction is addition of H. So for example, if we have 2 substrates of the same kind, so in the electron transport chain, you will hear about NADH plus H or NADH2. Okay, so we have a dehydrogenase enzyme, meaning it removes hydrogen. So in this case, it's called NADH dehydrogenase. And by the way, guys, this is the first complex. We'll talk about complexes in this story in a second. So this would give us NAD. We removed the hydrogen from NADH plus H and NAD, and the hydrogen or electron is put on a electron carrier. So here we lost H2, and this H2 is placed on a carrier. So we have two carriers, but I'll talk about that more in a second. We have the Q and cytochrome C. So in this case, this would be carried onto Q, and this is an electron carrier. So just to explain quickly, so this is the reduced form, while this is the oxidized form. Now, these two are called redox pair, and this is an example of a redox reaction where reduction occurred and oxidation also occurred as we removed a hydrogen. And by having that type of redox reaction, this will actually give us free energy. So this free energy will be used to pump protons, if you remember previously, across from the matrix to the intermembrane space. So this is where we get energy. Okay, so the complexes have two roles. Some of them have two roles and others have one. So in the case of some complexes, they act by removing a hydrogen, such as in the example in front of us, the NADH dehydrogenase. This removes a hydrogen, and the second role is act as a proton pump. While in a complex called complex 2, it just removes a hydrogen and doesn't play a role in pumping protons. While the third and fourth complex have a secondary role of pumping protons across the inner membrane and also play a role in transporting electrons across in the electron transport chain. So we'll talk about the four complexes right now, and we'll talk about the fifth one later on. So we have four complexes in the inner membrane itself, and these are integral proteins, meaning they are just proteins, and each complex of these has an enzyme. So for example, in complex 1, we have the NADH plus H, the NADH dehydrogenase, which takes NADH plus H and turns it into NAD. And it takes the hydrogen and it gives it to Q. So Q is a mobile electron carrier, meaning it carries electrons, or in this case, it's going to carry hydrogen. So when NAD gives it its hydrogen, it turns into QH2, okay? But we also have complex 2. Complex 2 contains an enzyme called succinate dehydrogenase, which takes succinate and turns it into fumarate. Now we have hydrogen, we give it to Q, and it forms QH2 as well. And we have FADH2, which turns into FAD, and it goes to Q and turns it into QH2. Now, when we arrive at complex 3, it accepts electrons only, meaning it doesn't accept hydrogen like Q, it accepts electrons only. And if you remember, the hydrogen is basically made up of one proton and one electron. So it splits the hydrogen which it receives from Q. So it now carries two electrons and it splits two protons into the matrix. And now once it carries two electrons, it gives these two electrons to the cytochrome C. Cytochrome C is also a mobile electron carrier. And what the mobile electron carriers do is carry hydrogen from a complex and send it to another. So in this case, we have complex 3 is going to carry two electrons from it and send it to complex 4. So we use the oxygen in this complex along with the two electrons that it received from cytochrome C, the mobile electron carrier, and the two electrons plus the two protons that were produced from this complex, because it couldn't carry the protons and it carries electrons only, are combined together and they form water. So we add half an oxygen atom and two protons and two electrons, which forms water. And this is the cell respiration which occurs, and this is one of the sources of water inside of our body that is synthesized. Okay guys, so now we'll talk about the chemiosmotic theory, and I gave you a simplified explanation of it. Now that we've taken the complexes, I'll explain it in more details. So each complex had a redox reaction. So in the first case we have the NADH plus H and the NAD. So this is a kind of redox reaction. And as I've mentioned, it gives us free energy. So we use that energy to pump protons across the inner membrane into the intermembrane. So the protons move from the matrix to the intermembrane space. Now, which of these complexes is able to pump protons? We have complex 1 and complex 3 and complex 4. They are able to pump protons, and complex 2 doesn't pump any proton. And it probably doesn't pump any proton because this reaction didn't release enough energy for it to be activated and actually pump protons. So let's draw it quickly. So we have in this one, we have the 4 protons moving from the matrix to the intermembrane space. And here we have 4 protons also move in complex 3 intermembrane space, and complex 4 is different. It only pumps 2 protons, so it moves in the intermembrane space. So now we have a total of 10 protons pumped inside of here. And this allows us to basically have more protons inside of here, and our goal is to return these protons through the ATP synthase. This thing, synthase. So once we return it through the ATP synthase, we basically form ATP. Now the ATP synthase is formed of 2 subunits. It's also called complex 5. It's formed of 2 subunits, the F0 and the F1. So the F0 allows movement of protons, so it's permeable to protons. And once we reach the F1 subunit, this is where the ATP synthesis takes place. So by 4 protons entering and only 4, we are able to form ATP by using the ADP and the inorganic phosphate in the mitochondria, in the matrix of the mitochondria, to form ATP. But in order to generate energy, we need that movement of electrons, of protons to occur. Once we have 4 protons pass by, it acts as a motor, as I've said it before, and this motor gives us just enough energy to produce ADP plus PI, and now we have formed the ATP. So you guys may wonder, and I've said it before, why doesn't it move back through the inner membrane space? Since I've already said this has a higher concentration, the intermembrane space, than matrix, why doesn't it just move back by simple diffusion? Well, as you can see, the inner membrane is impermeable to protons, so it doesn't allow movement of protons. So that's why we pumped them to actually make them move in the intermembrane space and return to the desired area, our motor, which uses 4 protons to make like a rotation and basically allows ADP and inorganic phosphate to form ATP in the mitochondrial matrix. Okay guys, now one final thing, I want to explain the movement of electron in the electron transport chain. So it moves from low redox potential to high redox potential, also called negative redox potential and positive redox potential. So in this example, we have things that such as NADH plus H and FADH2. This is the things we use to start our reaction, and we ended our reaction with oxygen in the electron transport chain by forming water. So if you remember, the NADH plus H gave its electrons or hydrogen to Q, and FADH2 did the same thing. They want to give up their electrons. They prefer to be oxidized, meaning losing their hydrogen. While in the case of oxygen, which was the final thing that we had, where we combined protons with electrons and oxygen to form water, this wants electrons, it wants to receive it. It's a great acceptor of electrons, meaning it prefers to be reduced. So this is the redox potential that we have.